Hey guys, so we're still in section 3.8. I'm on page 319 and I'm hoping that we can kind of wrap this up in this video. So I have just a few more applications of where we use exponentials just to kind of expose you to different ways that they get used. So another way that this gets used is temperature, and in this case I've got a can of soda placed inside a cooler. So we're told that its temperature T of x in degrees Celsius is given by the following function, where x is the number of minutes since the can was placed in the cooler. So we're going to use this function. So when it says find the initial temperature of the soda, what is it really asking for? The moment that you put the soda in. So how much time has passed? No time, right? So this is talking about the moment where x equals 0. So this is what we're really being asked to evaluate. So normally we need a calculator to help us with the E calculations, but in this case, so this negative 0.05 times 0, that's just going to give me 0, right? So this will end up ultimately becoming negative 6 plus 30 e to the 0. Anything to the 0 power we've already talked about is 1, so this becomes 30 times 1. And so if you just continue to work this all out, you'll get that this equals 24, and this would be degrees Celsius. Let's get a little better degree sign here. Okay, so that's the first question. Then it says find the temperature of the soda after 20 minutes. So now I'm just being asked to evaluate this at 20. So maybe you want to pause the video here and just evaluate that on your own. So let's see, if I plug in 20 for this, so now I've got to just kind of work this all out. So this might take just a little bit more work now. So negative 0.05 times 20, that'll give me just negative 1, and then you'll really just want to use a calculator to figure kind of the rest of this out. So let's see, 30 times e to the negative 1 is 11.04, I'll round up. And then if I add those together, this will be 5.04 degrees Celsius. So in 20 minutes, now it's gone from 24 degrees Celsius to 5.04 degrees Celsius. And then we have the question, do you think the soda will ever get to be 0 degrees Celsius? How can you determine this? So now I want to know, will this ever be 0 degrees? So I want to solve really this equation, right? Setting this equal to 0. Now, as I said, I'm not going to show you necessarily how to solve these types of equations. That would be for another class. But we can use a graph to figure this out. So notice if this equals 0, that's equivalent to finding its x-intercept, right? So here's my graph of this equation, and so I can see where its x-intercept is. It's right here. So now we just have to make an estimate. So this is what, at about somewhere around where x equals 32 minutes. If you try to estimate this is about 32 minutes, and if you plug that in, you'll see we get pretty close to 0. So it's once again another pretty good guess. So, okay, now let's talk about just maybe one last application here. Compound interest. So this is also an exponential equation. So notice here I have some like variables up here, so compound interest. So P stands for the principal, so that's the amount of money you're putting in the account. Rate is the rate as a decimal, so you want to make sure you convert if you need to. N is the number of times a year that interest is compounded, and T is the time in years. So I'll do one of these with you. So suppose $1,000 is deposited in an account paying 4% interest per year compounded quarterly, which means 4 times per year. Find the amount that is in the account after 10 years with no withdrawals. Okay, so we're starting with $1,000, that's my principal. Now, I was told that my interest rate was 4%, so that's 0.04. And then the number of times that is compounded, that's quarterly, so that's 4 times a year. So 0.04 divided by 4. And then all of this to the n times t, so 4 goes for n, and then this is after 10 years. So here's everything that would go into this calculation. So now we just have to go through and kind of work this out using the order of operations. So inside the parentheses, this will become 1.01. So now I just have to take that to the 40th. So, oops, now I get A equals 1,000 times, and granted this is just an estimate, but this is about 1.48886 and so on. So if I multiply that times 1,000, I get 1,488.86. Not surprising given this decimal. So this would be after 10 years, if this was how your interest was compounding, this is how much would be in that account without having to do anything. So now what I want you to do is I want you to do B, read it over, set the whole thing up, solve it, hit play when you're ready. Okay, so now let me go ahead and plug everything in. So this is 2,500, and let's see, this is going to be as a decimal 0.03, and it's compounded semi-annually, so it's twice a year, and then this will be 2 times 5. So there's kind of everything that goes into this. So now I'll start working this out. This comes out to 1.015. So now if I just take that to the 10th, I will get, let's see, 2,500. So again, this is just me doing a decimal approximation here. So this keeps going. So if I multiply this now times 2,500, I'm getting that the amount in the account would be 2,901.35. Okay, so that's working with compound interest. So now let's switch gears again to talk about another part of exponential functions and equations. Okay, so once again, I want to take a look now at just some patterns here. So I want you just to take a moment, pause the video, and what I want you to figure out is what is causing the numbers to go up, which tables have the numbers going up. So like here in the first table, what's causing those numbers to go up versus what do you think is causing the numbers to go down? Is that consistent with some of the graphs that we saw earlier? So pause the video, just think about this for a second, hit play when you're ready. So what you'll notice here is, as long as I have this number that's bigger than 1, so it doesn't matter what number, like here or here, it doesn't matter what number's in front. Look at the numbers. These are going up, these are also going up, right? So it's all about, just like before with the graph, it's all about what number has kind of that x exponential attached to it. Versus with these two, so notice I've got 0.6 here, numbers are going down. Same thing here, right? So once again, just to kind of point this out, this number here is not really driving whether or not the numbers go up or down. So that's just a very important distinction to kind of make. So we can summarize this. So when the number in the parentheses is bigger than 1, the y values are increasing. If it's less than 1, then the y values are decreasing. So this actually demonstrates the idea then of exponential growth and decay. So that's this next part. So using this form of our equation, we see that exponential growth occurs when our b is greater than 1. And this means that the value of the function begins to grow as we input larger numbers into it, versus exponential decay occurs when b is between 0 and 1. And this means that the value of the function decreases as we put larger numbers into it. So growth and decay, that's kind of the next thing that we're interested in. So with that in mind, we have another way that we kind of think about this equation, the way that we really can kind of view it. So we can think of b. This b is our growth or decrease factor, while the a, this a here, this is really our starting value. And we've kind of seen this already in some of the examples that we've looked at. For instance, if I were to plug 0 in for x, then the only value that gets left over is my a, so that's what's helping determine my starting value. So now I just want to get used to kind of working with problems like this. So I want to show you 2 problems where we're actually going to now write what the model is based off of the problem. So we're going to model the following situation with an exponential function. At the beginning of an environmental study, a forest covered in an area of 1,500 kilometers square, or a forest is covered in an area of 15 kilometers squared. Since then, the area has decreased by 4.75% each year. Let t be the number of years since the start of the study. Let y be the area that the forest covers in kilometers squared. Write an exponential function showing the relationship between y and t. So now that we have an example in front of us, I want to strengthen kind of what we were talking about before. So first things first, do we have growth? Do we have exponential growth or exponential decay? So is this increasing or decreasing? Well, we definitely see it's decreasing, right? Because we have this percentage. So what we have to do now is just understand when we are given these percentages, there's a certain way that you have to interpret them for exponential functions. So I want to go back up to this now that we kind of have an example in front of us, and I want to add on one more piece to this. So for growth, what you're going to do is you're going to take 1 plus the growth rate. 1 plus the growth rate. But for decay, you're going to take 1 minus the decay rate. So this is actually what's going to ensure then that our function is kind of going the way that we need. So we know that this needs to decrease. So decrease means that the b has to be somewhere between 0 and 1. It can't be bigger than 1. If it was bigger than 1, then it would create growth. So the structure of this then will be y equals, and now we have to have our starting point. So I just want to kind of write all of this out. So we've got our starting point times 1 minus our decay rate, and then all of that's going to be to the tth power. This is kind of the general setup that we're going to think about. So what's our starting point in this? Well, we're told that at the beginning of the study we have 1,500 kilometers squared. So that is our starting point. And then to get to the decay, so you're going to take 1 minus the decay rate, which is 0.475. So now you just have to simplify this. So the equation that would model this is 1,500 times 0.09525, all of that to the tth power. And so that's what we're looking for, is just to write the exponential function. So now I want to compare that to this other situation. So we're going to have to tweak the way that we think about this a little bit. So we want to do the same thing. We want to write just what is the equation that would model this. So at the beginning of a population study, not student, my bad, study. Oh, it's always so fun to make errors like that when you're making videos. So a city had 30,000 people. Each year the population has grown by 8.8%. Let t be the number of years since the start of the study. Let y be the city's population. Write an exponential function showing the relationship between y and t. Okay, so this is talking about growth now. So it's going to be a little different from the previous example, right? So what I want you to do is just see if you can come up with the structure of the model and write the equation, kind of using what you've learned so far about what it means to be growth versus decay. Hit play when you're ready. So in this case, I'm going to have the same idea. I'm going to have my starting point. But for growth, I need to take 1 plus the growth rate. So that's what I would have to do in this case. So there's the general structure. So my starting point is 30,000 and my growth rate is 8.8%. So here's kind of the general structure. So the final equation would be 1.088. So 30,000 times 1.088 to the t. Okay, so one last example. And this is something I learned about in like the last year. So I actually created this problem based off of watching a documentary on this situation. So we've talked about the idea of exponential growth, and we've kind of talked about how things can spread. And there's actually a really interesting documentary on this thing called the Fire Festival. Fire Festival, it's right here. You can totally look this up. It's on both Netflix and Hulu. Highly recommend that you consider checking one of these documentaries out. And So what the Fire Festival was it was a fraudulent music festival that was held in the Bahamas. And basically they sold out this music festival, but they didn't actually have any bands, nor did they actually have housing. So thousands of people showed up to this little island in the Bahamas, only to find that there was no festival, and it was like this big disaster. So it's a really crazy documentary. I highly recommend that you consider checking out one of them. But one of the things about it was this was the first time this festival was ever run. And so people really remarked on how quickly the word got out about it and how it became such a hot thing. And to create hype for the festival, so it's kind of the key part here, to create hype for the festival, 63 Instagram influencers were hired to post about the festival at the same time. So an influencer, if you're not familiar with the term, it's like somebody who basically has an Instagram or a social media account, and they just get paid to kind of advertise on it. So you have 63 Instagram influencers who were basically hired to post about this festival all at the same moment in time. And these people had millions and millions of followers collectively. So we're talking about some of the biggest Instagram accounts on the internet. This is actually a PowerPoint slide from the creators of the festival, of like just the amount of who they hired, and then like how many millions of followers they had collectively. So the reason that this festival sold out was because these 63 people created this instant buzz about it, and because of exponential growth. So now let's get to the actual math part. The promoters paid 63 influencers to post about the festival at the same moment. This is the moment 0. After 1 hour, 120 people knew about the festival. After 5 hours, 1,560 people knew about the festival. Can you create a model of this exponential function, and how many people knew about the festival after 24 hours? Okay, so we've got several pieces of information here. So I'm going to kind of walk you through how to work with this. So let's start with this first part. So if I have this structure, my y equals a times b to the x, where a is my starting point, well, I know that my starting point is these 63 people, right? So if I'm trying to figure out how the growth model for this festival, I'm going to use my a for 63. So now I just have to figure out what is my b to the x. And you might be thinking, oh, I can't do that. But look at this. After 1 hour, 120 people knew about the festival. So let's actually just plug this information in. So the 1 would go into the x spot, and the 120 people, that's how many people know about the festival, so that would go for our y. So check this out. If I set this up, 120 equals 63 times b to the 1. Well, what is b to the 1? B to the 1 is just b, right? So this is 120 equals 63b. So I can actually solve for b with this information that I have. So if I divide each side by 63, I get that my b equals, yeah, we'll round it to, we'll say about 1.9. Okay, so now I actually figured out my a and my b from this information. So I've got y equals 63 times 1.9 to the b, or sorry, 1.9 to the x, sorry. So now I want to figure out how many people knew about this festival after 24 hours. And this is a real statistic, by the way. I did not make this up. So we're going to use our model that we created now. So this is 63 times 1.9, so 24 hours. So if I work that out, let's see what I get. So if I plug this all in, I'm getting 308,622,064. So we'll just go ahead and say over 3 million people knew after 24 hours. So that's like totally a real thing. After 1 day, because they had these 63 influencers kind of start the buzz about this, 300 million, over 300 million people knew about this festival after 24 hours. That is crazy amounts of growth, and also ended kind of unfortunately. So there's a kind of a fun real world example for you, and that will cover this section. Thanks for watching.